Hello and welcome to the next session on Danveit-Hardenberg notations. After learning this session, you will be able to explain DS parameter to represent link and joint parameters. In 1955, Danveit-Hardenberg first time introduced the notations for robot transformation. They are very useful when we want to transform one frame to the next frame. Now let us understand various parameters that define the link and joint parameters. Now, as we have already seen the link, we have already seen different types of joints which are made to form a robot. Now, we have to learn now how to represent various parameters that will be useful for transforming a frame from one location to another location. The reason, one more reason for learning this is to know how exactly when we move from one axis to the other axis, what are the various parameters that are important to understand. So let us start with that. First is the length of the link. Length of the link. We represent it by AI. Length of the link, it is a mutual perpendicular distance between the two axes. Let us say this is axis I, this is axis I minus 1, this is axis I minus 2. Axis I, as can be seen here like by dotted line, chain line. The axis I minus 1 is a horizontal line and the axis I minus 2 is also vertical line. Now the length of the link is a measure of perpendicular distance between the two axes. For example, as you can see here, perpendicular distance between this axis and this axis is AI. This is AI. Similarly, the distance between this axis and this axis is here, that is AI minus 1. Second parameter is the angle of twist. It is measured by alpha I. Alpha I, it is defined as the angle between the axis I minus 1 and axis I. Now where is I minus 1 axis? I minus axis is here. I will mark it here. Axis I is over here. Now how to find out the angle made by axis I minus 1 between axis I minus 1 and axis I? Now suppose I want to know alpha I, that is the angle made by axis I. What I will do, I will move this axis I and intersect with the axis I minus 1. So this axis I minus 1. So I will move this I, suppose I is here and I minus 1 is here. So I will transfer this I over I minus 1. Now the angle made by I with I minus 1 can be seen here as anticlockwise. That is why this angle will be a positive angle, because we generally have a notation that anticlockwise is positive. So the angle made by axis I with I minus 1 is alpha I. Similarly, if I want to find out the angle made by I minus 1 with I minus 2, so I will again transfer this axis over here, like somewhere that will be somewhere here. And the angle made by axis I minus 1 with I minus 2 will be a clockwise here. So in this case, the angle will be negative, and here angle will be positive. Third parameter is offset of the link I, that is we look at DI. The offset of the link DI, it is a distance measured from a point AI minus 1. So AI minus 1 is over here, right? So we have seen the mutual perpendicular distance AI minus 1. It is intersecting, suppose, over here. Then the second, the length over here. Now what I will do, I will transfer I, that is AI, to a point of intersection of the ai minus 1 with the axis I minus 1. Like this is parallel. So this line and this line is parallel to each other. So wherever the earlier length is intersecting with I minus 1 and this length where it intersects with I minus 1. So this length is called di. This is called the offset of the link. For example, let us take our hand. So this joint is serially connected with this link and this link. So there is no offset here. But imagine if this link is at some distance here, so there will be offset di. We will look at in the example to follow. The next parameter is a joint angle. Joint angle is defined as the extension of ai minus 1 and this one is theta I, and this is generally a variable. This variable theta I for a revolute joint and for a prismatic joint it will be a di. Let us look at this. Very important point to note here. In case of revolute joint, theta I will be variable, and in case of prismatic joint, di will be variable. Now, how to find out the direction of y-axis and how to look at and how to mark the z-axis. Okay, suppose this is a z-axis of this axis here. I mean, we generally denote the axis about which the joint rotates is a z-axis. For example, this is a z-axis here, and this is zi minus 1. This is, I mean, this is the axis of rotation that will be zi minus 1. So if zi minus 1, that is this axis, and this axis intersect each other, then x-axis, right? Because this is a z-axis, and we are now interested in locating the x-axis. So the x-axis can be located by the two rules which are mentioned here. One is if the zi and zi minus 1 they intersect with each other, then x can be selected along either of the two remaining directions. Okay. Now in this case, as you can see here, this one is the zi minus 1 and this is zi. Okay. So one is like this and one is like this. So obviously they will not intersect with each other. Okay. So in that case, we can consider x-axis in either of the direction, either over here or in the other direction. Okay. So if, and the second rule, if zi minus 1 and zi acts along the straight line, okay, so that will happen sometimes because when we have a two revolute joint in the same direction. So if they are in the same straight line, then the x can be selected anywhere in the plane perpendicular to them. So if they are, suppose if this is zi minus zi and this is zi minus 1, so we can select the x in that plane anywhere. Now, once we know the z-axis and when we mark the x-axis, we have to find out the y-axis. Now, y-axis can be found out by using a cross product. That is, if this is z and this is x, direction of y can be found out by using a cross product. So, how we do that? Right hand rule. Okay. Suppose this is your z-axis, this is your x-axis. The direction of y is away from the observer like this. So, in this case, the direction of y-axis will be like this. yi. Okay, so y will be equal to z cross x. Now, once we know all the parameters, okay, so let us look at the various parameters. Theta I is the joint angle, di is the offset, alpha I is the twist angle, and ai is the length of the link. Now, when we want to find out the transformation, generally the transformation is followed with this. We will look at this in the following session in detail. So I'm just showing how relevant these parameters in order to find out the transformation. Suppose I want to find out the transformation of I with respect to I minus 1. That is when one axis, Okay, when one frame has to be transformed to the second frame, that requires four parameters. That is parameter 1, parameter 2, parameter 3, and parameter 4. Now, if you look at this parameter, for example, how we define theta I? Theta I is about the z axis. So, obviously, theta I means rotation. So, we define a rotation matrix about z axis by how much angle theta I, then followed by the translation along z axis. If you look at here, okay, translation along z axis. So, I want to find out the translation along z axis by how much, that is di. Then next one is rotation about x axis by how much angle, alpha I. And the last one is the translation about x axis by length of the link, that is ai. So these are the four parameters, and these are the axis, z axis, and this one is the x axis. So when we want to find out the transformation from one axis to the another axis, we have to follow these four set of transformation. And if you look at, this is rotation z and translation z. We define as a single term called screw z. That is, if you tighten the screw, how we do that? We first rotate and then it translates. So there is a rotation and translation. So screw z. Screw is rotation and translation about z axis. Similarly, the next one is a rotation and translation about x axis. The rotation x, translation x. So simply I define any transformation from one axis to another axis by screw z into screw x. That will define the complete transformation. And if you find the multiplication of all these parameters and multiply the matrices, you will come across a common composite matrix like this. We will learn that in a following session. Now let us take an example to understand in detail how we apply the DS parameter. For example, let us say the base axis is Z, Y, and X. Okay, and this is our base. Okay, then the next link is our twisting link. We call it a twisting link. Then this is a prismatic link. So how we understand that? This is a rotation, so there is a twist. Then when there is a translation, there is a prismatic link, and this one is this joint, right? This joint is our rotary joint. So how many joints are present here? One, two, and three. Okay. Then some dimensions are shown over here. That is this one A. This A is fixed one. Okay. Do you remember that first joint, that is rotary joint or a twisting joint? So in that case, this becomes fixed. It will not vary. Whereas this one will be a variable b, because there is a link which will translate up and down. Then third one is the rotary joint. Now the length of the link here is c, the length of the link here can be seen as here as b, because we don't call it as the length of the link, we call it as the offset, and it's a fixed offset here. Now we want to find the DS parameter for this serial robot. So how we apply it? Let us look at this example in more detail. Let us say a twisting joint. Now twisting joint, the axis as can be seen here is vertical. So I define the z axis over here. Okay, like this is a base, right? Z0, Y0, and X0. This is not a frame. Frame 1 will start over here. Okay, this is frame 0. This is frame 1, this is frame 2, and this is frame 3. I will tell what is meant by a frame. So whenever we want to move from base to the end effector, this is the end effector, we have to move with the parameters, right? That is rotation, translation, and so on. Now these are base axis Z0, Y0, and X0. Now I want to know, when I move from this point to this point, what are the parameters that will define the motion? So for that, this joint I have to define one frame. So I will define the frame over here. Okay, so this is our frame one here, and z-axis I will show as there is a rotary joint, right, like this. So I will provide z-axis like this, and since this z and this z are coinciding, so I'll just take the x-axis just to maintain the reference parallel to the x0, that is x1. So I define a z0, I define x1. Now once I know z and x, I will find out y that away from the observer going in the paper or in the screen, that is y1. Okay. Now the next frame is over here. The reason is because this is a joint. So first joint is here and I define the frame over here. Second joint is here, I define the frame here. So I have to move from this point to this point, this to this. So here I define, now how I define the z-axis here. Now if you look at the z-axis here will be like this because it is having a rotary, for example, like just imagine like this, right? Imagine like this. So it is rotating like this. So the axis is horizontal. Okay. So that is why the axis shown z2 is horizontal. Now, how I define x2? So look at this. Z1 is like this, Z2 is like this. So they are intersecting. So how we define? We can show in either way. I can show x like this or x like this. So I can define in any of the way. Okay. So I can show x2 like this also. Okay, this is horizontal line. Okay, I can show x2 in opposite direction also. But just to maintain the direction or we parallel with the earlier x-axis, I will maintain in the same direction. I am not changing the reference, but I am just setting the axis as the previous, that is x2 here. So once I know z, once I know x, how to find out our direction of, like this is our z-axis, this is our x-axis, so y-axis will go down. You can try it with the right hand rule. So y-axis will go down. So y2 is downwards. Now the next, remember the last frame is always provided to the end effector. So the end effector is somewhere here. So I define now over here the x, y and z axis. So the end effector now, just imagine that it is having rotary motion like this. So it will have the z axis just to maintain the, now it may happen that the end effector may not have a rotation or it will just a fixed. So we need to have just a axis for orientation. Okay, orientation. For example, I want to pick something. Okay, so for that the body frame has to be properly defined. So I just define the z-axis, z3. X I maintain the same as the earlier one, and once I know z, once I know x3, which is same as the earlier, I define the y3. So I have defined all these axes now. Now how to find out the DH parameter? So frame 1, frame 2 and frame 3. So I'll again go back. So this is frame 1 over here, frame 2 over here, frame 3 here. So I have to find out theta I, di, alpha I and ai. So what is di here? What is theta I here? Theta I is theta 1. So this is theta 1. Okay. Then what is the next parameter? Offset. Offset is ai. This star is for fixed offset. So we have seen that this is a fixed offset. Fixed offset, right? This is fixed offset. Alpha I is 0. What is meant by alpha I? Twisting angle here. Twist angle is the angle between the z-axis. Okay, so look at this. So here, the twist angle is 0. What the reason is z1 and z2. Okay, so as can be seen here, they are intersecting with each other. So that is why the twist angle is 0 here. And last one is the length of the link. This z0, right? So I'll just tell you once again why the twist angle is 0. Z0 is like this, Z1 is like this. So they are in the same line. So there is no angle between them. That is why the twist angle is 0 here. Length of the link for twisting angle is always 0. The reason is it is not having the reference with the previous. Okay. The length of the link is measured between the z-axis. Okay, so as we have seen in earlier case. So since z1 and z0 are coinciding, so there is no length of the link. Okay, now coming to the next frame 2. For next frame 2, okay, over here, the obviously the joint angle will be a theta 2 will be a variable. Sorry, this is a prismatic frame, a prismatic joint. So for prismatic joint, there won't be any theta I, but there will be a variable b, that is this b will be a variable here that is moving up and down. So this variable b is measured for di. Now coming to important alpha I. Alpha I is the twisting angle between the z axis. Now why it is minus 90? Look at this. Z1 is vertical, Z2 is horizontal. Now what I will do, I will move the Z1 in line with that, right? So what I will do, when I want to find out Z2 with respect to Z1, Z2 with respect to Z1. So I will move Z1 over here. Okay, this is Z1. The angle made by Z2 with the Z1. Okay, so look at this. Angle made by Z2 with Z1 is clockwise, and this is 90 degrees. That is why the angle here is minus 90. The length of the link, distance between the z-axis, again they are intersecting. So when the z1 and z2 intersect, the length of the link is also 0. Coming to the last frame is somewhere here. Okay, now here is a rotary joint. So obviously the joint angle will be theta 3. How I represent that? Theta 3 over here. Theta 3, this is our joint angle. Offset is 0. Okay, so how we measure the offset? We measure the offset, the distance between the x-axis, because x2 and x3 in the same line. So there is no distance here, so offset is 0. So do you remember how we find out the offset for earlier? So distance between the x-axis, like b and a, these are the distance between the x-axis. Like for example, for the first frame, the distance is here a, for the next frame is b. Now since here x2 and x3 are on the same line, the offset is 0. Twisting angle also is 0 here because Z2 and Z3 are parallel with each other. So there is no twisting angle. And last one is the length of the link. Length of the link is measured, the distance between the z-axis. So here the distance between the z-axis can be clearly seen as uh, c. So that is why the length of the link is c. Okay, so this is about the earlier one. There is a small variation in the another example. So this example, earlier example, if you look at here, this is a twisting joint followed by prismatic joint. Now in this case, it is the prismatic joint followed by rotary joint. Okay, so we can again define the same way. That is Z0, Y0, and X0 is the base frame. The first frame over here, and this is Z1. See, prismatic link moving up and down like this. So Z will be in that direction only. So Z1, X1 I maintain the X0 parallel to that, and Y1 perpendicular to it. Then next one is this horizontal axis, which is same as the previous example. So there is no much change here. So I will not explain in much detail. You can just have a look at the DH parameter. So for DH parameter, since the first frame is a prismatic frame, theta is 0, whereas this is rotary and this is also rotary, so there will be a theta 2 over here and theta 3 over here. So we can observe that theta 2 and theta 3. A and B will interchange. This is a variable and this is a fixed. So this is variable and this is fixed. alpha I for second is minus 90 and same as the earlier. So this is how we have seen the example for representing a DS parameter. So this is all about the session on the DS parameter representation. In the next session, we will see how to apply DS parameter for various kinds of robots. Thank you.